Okay, so part 3. Okay, so for the first half of today's lecture, I'm going to discuss some proof ideas of the theorem on the board, which was where I finished last time. So this is joint work by myself and my graduate student, Ben Call. Okay, so it's the same setting we've had all week, geodesic flow on a closed rank 1 manifold. We have a potential, it's either Holder continuous or it's scalar times the geometric potential. If we have this pressure gap, well, the unique equilibrium state was provided by BCFT, we talked about that. And now I want to talk about this unique equilibrium state must have the Kolmogorov K property. So this is one version of the definition. Whatever partition you put on there, as long as it's not equal to the trivial partition, mod 0, has positive entropy. That's one definition of the K property. Another reformulation of this is that the K property means that the system has a trivial Pinsker sigma algebra. The Pinsker sigma algebra is essentially the largest zero entropy partition. This says that is that. Okay, so what's behind this theorem? I gave some hints last time. The main tool that we have is some rediscovered gold from the body of work of Francois Le Drapier. So let me tell you what that is. So our main tool. I'm going to write it for continuous time, so I'm going to say after Le Drapier. So Le Drapier's version was discrete time. We need the continuous time version. So it says XF be flow on a continuous flow in a compact metric space. We need some weak expansivity. I'm going to write asymptotically H expansive. If you don't know what that means, don't worry about it. It's just a weak expansivity condition. We certainly have it in our setting. It's weaker than entropy expansivity, which we certainly have. And what we're going to do is we're going to consider the product of two copies of the flow. Be the flow given by two copies of XF. Okay, and I want to be completely emphatic. We're not thinking about an R2 action or anything like that. We're really thinking about a flow. So, it's the system. We just got one parameter, and we're just sending each coordinate but by the same S, right? For all S belonging to R. Okay, so we're considering the product system, and then we're going to put a potential on this space as follows. Phi tilde from this product space, it's just going to be just add the value of the original potential in each coordinate, or I should have probably said got a continuous potential there, so we lift that in a natural way. So these are all hypotheses. The statement is if phi tilde has a unique equilibrium state, of course I mean for the product system, then the unique equilibrium state for the original system, if there's a unique equilibrium state here, there must be a unique equilibrium state here. I'll clarify that in a moment. It's the important conclusion, has the K property. So this is this really extremely nice insight connecting, uniqueness of equilibrium states and this Kolmogorov property, this very strong mixing property. If you get uniqueness on the product system, you get the K property on the original system. Let me try and give some insight into why this is true. Francois did this in the discrete time setting, and I guess our proof is to reduce to that. It's actually the same trick that this Agnieszka showed a couple of days ago, attributed to Federico Rodriguez-Hertz. There's a trick there about reducing to the time 1 map or time t map. We can use the same trick here. So what's the proof idea for the original discrete time system? Let mu be the equilibrium state. On the original system, one must exist by the expansivity. Then we can see quite easily that the product measure is an equilibrium state upstairs. I mean, this is just a simple calculation. Let's do it. So entropy of the product plus the integral of the product, just 2 entropies plus 2 integrals equals twice the pressure. And this is the pressure upstairs, right? Just some basic stuff. Okay, so we definitely already have one equilibrium state upstairs. So if you have a unique equilibrium state, that's our hypothesis. It must be mu times mu for the unique equilibrium state downstairs. And we must have a unique equilibrium state downstairs. If there was another one downstairs, we could form that product, and that would contradict uniqueness in the product system, right? Okay, good. So we have a candidate here. So what's the idea here? What's the connection with the K property? Well, if mu is not K, there exists a non-trivial Pinsker sigma algebra. As I just said in words, this is the biggest zero entropy partition. I won't write out the details here, but if you have this, you can use this to construct another equilibrium state upstairs, thus contradicting uniqueness in the product. It's a very nice little argument. Okay, so yeah, I just wanted to give you an idea of how that worked. I mean, also just something to kind of make the whole thing sound plausible. It's a very long-standing strategy, to look at the product measure to get, the product system to get stronger properties on the original. I mean, the classic example of that is that one characterization of weak mixing is proving ergodicity of the product system, right? So that's another bit of intuition. Okay, so once we've done this translation, okay, so how does one get the K property? Well, okay, who knows? But now we have this. We've reformulated the problem as being a uniqueness of equilibrium state problem. Great, this is in my wheelhouse. Okay, so what's our strategy then for showing the K property in this setting here? Well, I think given the general thrust of these lectures, it's pretty clear we're going to have to show unique equilibrium states for the product system. And if we can do that, we're going to have the Kolmogorov K property, and then all the things this implies, like mixing of all orders, and all the things below that. And certainly in the measure of maximal entropy case, we can even go up, all the way up to Bernoulli. Okay, so how are we going to do this? Well, how do we get uniqueness downstairs? Well, you know, it's this theory of decomposing the orbit segments I was talking about last time. So, you know, what are we going to do? That's what we have to do. We need to find a decomposition on the product system. Okay, good. There's a problem. A pretty big problem. So what is a decomposition? You know, it's some way, you know, in our abstract stuff, you know, we just defined it as some way to chop up an arbitrary orbit segment into three pieces, you know, good stuff in the middle, bad stuff at the end. And in our general stuff, you know, we just say, okay, suppose there's some way to chop it up that satisfies these hypotheses. Boom, we can do things. Well, if you define decomposition like that, unfortunately, lifting the decomposition to the product does not work. So that is a pretty serious problem. And you can see the issue if you start thinking about the symbolic examples that Vaughn was talking about last week, beta shifts, or you can see it really clearly with S-gap shifts. I mean, what do we have going for us? Well, if you have G with lots of good properties, we can certainly hope that G times G has lots of good properties. Yeah, that's probably going to be okay. But you need to find it as part of a decomposition. You know, what if your two good orbits don't line up properly? You know, you've got no way to chop back to that good core. You know, that there may be no way to chop back so you have a nice G cross G in the middle. And you know, if you start playing around with an S-gap shift, you're going to see that this strategy looks disastrous. So you know, the original class of systems we were looking at, these symbolic things that in many ways are simpler. You know, this strategy just is doomed to fail there, it seems. I think it's doomed to fail there. Okay, so what do we do? Can I delete bouillabaisse for dinner? I'm excited about this, but I think the message is out.
Just don't pass that on to
Okay, so doing this for a general decomposition is not going to work, but what if we ask more in our definition of decomposition? We're going to define something which I'm going to call a lambda decomposition, and this is going to be a decomposition coming from a function let's say continuous function lambda from the space to 0 or infinity. So this is the kind of decomposition we had in this situation here, right? It was all about this function lambda to do with curvature of the horospheres, and I showed you last time how to turn that into a decomposition. And in fact, Vaughn was using the same idea over and over again last week as well. So things with lambda decompositions, as well as including this, it also includes the Manier example. It includes these partially hyperbolic systems with 1D centers, where lambda was growth in the center direction. It includes this setting. It includes geodesic flow with no focal points, which generalizes our stuff, at least in the surface case. That was carried out recently by Chen, Park, and Cow. Okay, so that's what we're going to do, and I claim that when we do that, things do work well in the product. So let me define lambda decomposition formally. Again, this is one that I prepared earlier. Oops, so let's move this. Huh? Oh, uh-oh. Okay, that's going up. Jammed. Oh no, oh no, okay, good. Okay, that one's stopped. Okay, so here's something I thought I should write up formally what I mean here. This is an idea that I sketched last time. We can set this up abstractly. So continuous flow in a compact metric space. We got this function lambda. Formally, I can just make this a definition, right? In practice, of course, we're going to need lambda to actually tell us something. As I said last time, we should interpret it as somehow measuring hyperbolicity. But formally, I can just make this definition. I've got some reference function. It can be continuous, or it can be bounded and lower semi-continuous to include characteristic functions. My bad stuff at scale eta is just going to be the stuff where the average is less than eta. The good stuff is going to be the average is greater than eta for all initial and terminal segments. So just like we did last time, I'm sure Vaughn did this construction last week as well. And then the rule for decomposing something arbitrary is you just start looking from the beginning, go along as far as you can until the last time you're in B eta. That's where you decide to chop. Symmetric operation going from the end. What's left is a good core satisfying this property. Okay. So I claim that a decomposition defined in this way does lift well to the product. So what I'm going to do for application to a product system, I'm going to define a function lambda tilde from x times x to the positive reals. Oops, lambda tilde xy is equals to product lambda x, lambda y. And my strategy is that a lambda decomposition for my original thing is going to give me a lambda tilde decomposition on the product. So we have to change the eta a little bit, but that's no problem. Okay, so what does this do in practice? Let me think about an orbit segment in the product system. So I guess I'm thinking about an xy comma t. I'll draw it like this. These are the two coordinates. And so what am I doing? I'm doing what I normally do. I go from this end, and I just cut, and I cut, and this is where all the averages are less than eta. And then, so I'll do this. So average of lambda tilde less than eta. Same here. Average of lambda tilde less than eta. And then along the middle segments, average always greater. Right? So that's what it's doing formally. So how does this match up with the original system? Well, the good news is that in particular, at these endpoints, lambda tilde is uniformly positive, and of course that gives you that lambda is uniformly positive in both coordinates. So that's the good thing that's happening for us with this definition. So if we believe that lambda being uniformly positive will give us some specification property and lots of nice things, then we might believe that having lambda uniformly positive in both coordinates is going to do good things for us in the product system. That's exactly what we do. Okay, but how much are we chopping out? Well, let's think about what we chop out. Well, what things have average less than eta? Well, certainly in particular things which have average of lambda tilde equals 0. That's certainly less than eta, right? What things can be like that? Well, we might end up chopping quite a lot out here because if lambda vanished on this coordinate, that would give me freedom to put anything that I like in the other coordinates, and I still need to chop that out, right? So it looks like maybe we have to chop out a lot of stuff to get this good core. So how much stuff are we chopping out? Well, I claim that at best, and actually, what actually happens is that the pressure of the prefixes and suffixes is going to be like the pressure of the whole space plus the pressure of the prefixes and suffixes downstairs. That's a phi tilde. Right, and that's reflecting the fact that you know, we can allow anything in one coordinate while the other thing vanishes. I mean, obviously, there's a bit of argument to get this, but you know, this is what's going to need to happen. Okay, maybe that looks bad. That's quite a lot of stuff, right? But something saves us. We're in the product system. This is okay because you know the pressure of the product system equals twice the pressure downstairs. So we've still got a gap. Yeah, and for discrete time applications, but basically that's the story. We work with this decomposition, and we can get uniqueness of the product system. Gives us K. Yeah.
What happens when you do the specification?
Yeah.
You've got sort of variable time.
Well, that would kill you.
Oh, so you need both factors to come back?
Yeah, you absolutely need exact time in each factor. Yeah.
Because when your theory usually allows time less than equal to some.
Yes. 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 But for this, we need exacts for sure. Yeah. Yeah. Which we have. Yeah. Yeah. Thanks. Okay, so if we were doing discrete time, this would be more or less the whole story. We have estimates on specification, regularity. We have an estimate on how much stuff we're chopping out. But actually, in the flow case, we are not yet done. And what we haven't done yet is actually the hardest bit by far. And this is issues related to expansivity. I'll try and give you some flavor of what's going on with that. Okay, so much more serious problem. So finding the product decomposition was okay. Thinking about expansivity, okay. We have a serious roadblock. We're going to have to do some work. So let's recall the issues here. We can look at the set of points. This is like the bi-infinite Bowen ball. The set of points which stay close for all time. Okay, and you know we have to. And yeah, so if we're doing discrete time, you know, expansive behavior means that this is just a point, and what we asked for is that, you know, the set of non-expansive things, you know, will have measure 0 with respect to an equilibrium measure. Okay, but in the flow case, remember that. We're going to define the non-expansive set for a flow is going to be the set of X such that this set does not equal an orbit segment. Right? Because in an expansive flow, we're expecting the set of points that stay close to X, you know, to be a little piece of orbit. So non-expansive points is not that. And so the general theorem that I stated last time, it was all conditions on, I had this notion of pressure, of obstructions to expansivity, and it was all defined in terms of this set. Okay, but what about for a product of two flows, which is what we have now? The non-expansive set for a point, I guess a point now will have two coordinates. Well, it's always going to contain something like this for some small value of s. Okay? In other words, the product flow has a two-dimensional center. So if I draw there's my two coordinates, so my y lined up. So we have to allow for a point whose first coordinate is there and whose second coordinate is there, and that should stay close for all time, right? How big a deal is that? It immediately throws all of our old abstract results formally out of the window, because everything's going to be non-expansive set. Everything's going to be in the non-expansive set in our previous sense. So we really have to dig into the theory in a serious way and build a new theory adapted to this. That is, we have to build that controls. I guess we can use the notation NE with a cross for product, epsilon f times f equals a set of x such that so non-expansive things in this sense will be things that don't collapse, maybe S1, S1, things that don't collapse onto a product. Okay. This is the best we can hope for, right? Okay, and we do that. How serious are the issues? Well, they're pretty serious, and let me give you a sense of them. Okay, one thing that is not serious is growth rate estimates. Growth rate estimates, no problem. Things still appear at a scale. You can still do your counting estimates. That's not a big deal for that. I don't know if Vaughn discussed this in the lectures last week. It was certainly in the supplemental notes he put on the conference wiki. So after you've got uniform estimates on partition sums and things like this, actually the hardest part of the abstract uniqueness proof is constructing what we call an adaptive partition. So we get some kind of Gibbs property, but we want to use that, right? And we build this candidate equilibrium state, and we need to show this is ergodic, and we need to show that there's no space for a mutually singular equilibrium state. And we do that through using the Gibbs property, but a major step is building a partition whose elements look a lot like Bowen balls. And then you can change estimates on Bowen balls into estimates on partition elements. So we need to, okay, so what happens, well, it's all about what Bowen balls look like. I'll use some notation which people don't use that much, although I wonder why, because it's very convenient. So So I'm going to use this notation for a two-sided Bowen ball, things that stay close for time, whoops, minus t up to t. So it's all about what this looks like, right? And in discrete time, you know, if you're expansive, you know, this is going to look like a pixel. It's going to be a tiny box. And at some point in the argument, you know, we need to approximate a set of positive measure or something like this with elements of a partition that look like this. And so if these things are collapsing down onto pixels, we're going to be able to do that. Life is good. Okay, so what about flow? So discrete time, this is going to look like pixels. Well, this is going to collapse down onto a little bit of orbit. And this is going to end up looking like, not a pixel, but a thin cigar. Is that good for us? What can we approximate with stuff like that? Well, we can still approximate invariant sets. You can still approximate invariant sets with things that look like thin cigars. And that's enough for us in the flow case. You know, what do you need to do for ergodicity? You need to say something about the measure of invariant sets, and we can still control them with partition elements like this. But what about our product flow case? What we get is that this looks like, well, it's going to look like, you know, a neighborhood of a two-dimensional disk. What can we approximate with that? Well, we can approximate sets that are invariant under the R2 action, i.e. invariant under every fs cross ft. Yeah, that works. Does that give us ergodicity? No way. So, you know, using the same techniques we had before, we have the ability to control you know, a very restricted class of sets, and that's not enough for us, and we need to get some new ideas, particularly for our ergodicity proof. So we build this candidate measure. It's just going to be mu times mu for the guy downstairs. That's our candidate for uniqueness upstairs. And the hardest thing about our arguments in this regime is getting ergodicity. So we need ergodicity for product measure. Well, that's weak mixing, right? Our way through this was proving weak mixing downstairs. We were able to prove some kind of mixing estimates downstairs and combine it with a spectral argument to get weak mixing, which then gives you ergodicity on the product. Yeah. Okay, so this argument, we have this written up in a you know, pretty complete manuscript. It's not on the archive yet. I'll be happy to share it with anyone who wants to see it. Just send me an email. We're sitting on it for a while longer because we're still figuring out all the details of the Bernoulli application. I should also say that you know, we're working in this flow setting. We're chasing down, you know, this application that's really interesting to us, the geodesic flow. My student Ben is also writing another paper which is going to take care of the discrete time case as well and apply it to a bunch of these other settings we were talking about. Okay, so I have 15 minutes. So in my last 15 minutes, let me start my third lecture. Having 3 lectures to give is a very dangerous thing. You think, this is great, I have 3 lectures. And then you prepare 5 or 6 lectures of material. It's a disaster. Okay, so my final topic, which I certainly won't be able to get in as much depth as I was hoping to, but I have written this up in the notes that are on the conference wiki, so I certainly invite you to have a look at that if you're interested. So, you know, I want to talk about this really key thing that makes all our stuff go in the geodesic flow case, which is the so-called entropy gap. And as discussed, the entropy gap is not a new result. It came from Knieper's arguments as a corollary of uniqueness 20 years ago. But that proof, you can't really see where the gap comes from. So we want to show by more direct and constructive means that the topological entropy of the geodesic flow is greater than the entropy on the singular set. Let me just point out something which should really be pointed out. In the surface case, there is nothing to do here. So if mu is a measure supported on the singular set, let's say ergodic just for ease, then the entropy equals 0. This can easily be observed by the Ruel inequality and the fact that there's no expansion on the singular set for a surface. So use the variational principle. This is going to give us that the topological entropy on the singular set equals 0. Great stuff. So surface is no problem. However, in dimensions greater than or equal to 3, we most certainly can have that the entropy of the singular set is positive. And the reference, the basic reference for this phenomenon is the Gromov example. If you still remember that picture, the set of things that stay on one half of the construction are in the singular set. Such orbits have positive entropy. And so, it wasn't clear at all, I think, before Knieper that you should definitely even get this entropy gap. And somehow that this is, a really, really central issue. Okay, so let me move away from geometric considerations for 5 minutes and talk about how one can hope to produce entropy. I mean, the idea is very simple. If you have the specification property and, you want there to be entropy, somehow you just build by hand exponentially many orbit segments. You just do it. You just demonstrate it. The prototype of this is extremely simple. Let's think about a shift space with specification. The strong specification, so you have exact words. A simple proof, almost an exercise, prove that such a space has positive entropy. How do we do that? Take 2 different words in the language of the shift space. Let's imagine a grid of windows, and this can be length t maybe, and in each of these windows of length, I guess t plus tau, if tau is the transition time in the specification property, we'll just put in a word here, we'll put in a word here, we'll put in a word here. Each of these words is either W1 or W2. And we use the specification property to close that up into a word that's definitely in the language. Great. 2 choices here, 2 choices here, 2 choices here. So if I had n windows, this would give me 2 to the power n words of this length. Look at the growth rate. We have positive entropy. Great. So this is the prototype for using the specification property to create some entropy. You just build the stuff. So the next thing I do in my notes that are up on the wiki is to push this idea to a statement that's not terribly interesting, but contains the main idea. I don't think I will write this out because of time. but the theorem I have in the notes is, take a shift with specification, take a proper subshift, then the proper subshift has less entropy than the whole space. How are we going to do that? So I've got a shift with specification. I've got a subshift with no further conditions. I claim that the entropy of Y is less than the entropy of the whole space. And the way I'm going to do this is I'm going to fix a word W, which is in the language of the big space, but not the language of the little space. And basically what I do is I take lots of words from here, lots of words with the right growth rate, and somehow I use specification to mix in this word in a judicious way and show that the amount of things I can create is growing faster than the amount of things in here. The argument is actually a bit technical. One has, you could think about just being naive and doing this kind of thing. Take a word and keep on gluing in copies of Y or not in each window, and for a single point that's going to create exponentially many new things. Now there's a serious problem, which is that every time you do this, so we take a word here and chop out that much information to either glue in a W or not glue in a W, we've lost some significant amount of information. So once we start varying over all the different Y's that can go in here, you've got a drop in multiplicity corresponding to that gap. And if we make too many gaps, that's losing too much multiplicity, and the things that we gain are beaten by the loss of information. So the way around this is to choose, I need to just say, so we're going to take a window, let's see. So we're going to fix an alpha, choose alpha n minus 1 points from creating n windows Okay, so I'm thinking about, a kind of abstract time window, 0 up to n, well, n times n, chopped into, these are all my windows. This isn't an actual orbit, this is just some kind of schematic. And on some of these windows, I'm going to select them, and the sites we select, we're going to do this construction of inserting things. And what we do is we fix some small alpha and select that proportion of points. So maybe I selected this one, maybe I selected this one, maybe I waited a long time, then I selected this one. And with this configuration, I'm then going to play this sort of game. For the ones I've chosen, let's insert a W here, let's insert a W here. Well, it's edit, it's delete and insert, and we can build a new point. Where does the exponential growth come from? We carry this out over all possible configurations of choices, if we're choosing a proportion alpha of all of the possible places. So our estimates then end up with with an n-1 choose alpha n-1 term, and this grows exponentially. And if alpha is chosen small enough, this term is going to win over the multiplicity that you use. So that's all. Okay, so I have, I think, 7 or 8 minutes. So that was the basic idea for building entropy. Probably went a little bit fast, but this is all in much more detail, written out on the conference wiki if anyone wants to see what I thought I'd be saying. if I had managed my time better. Okay. But okay. So there's some stuff. There's some combinatorial arguments. The main takeaway is that if you have specification, you can build new orbit segments, and that's what's going to produce entropy. The details of that I was trying to give some hint of, but the main thing is that if you can glue things together, maybe you can believe that we can build more entropy. Okay, so let's get back to geodesic flow. Let's try and do the same thing. Well, okay, good. Let's try and do the same thing. So we want to start with the singular set, build more entropy. Immediate problem. Things in the singular set no way have specification. So how am I going to start building? Well, what we need to do is we need to approximate things in the singular set by things in the regular set. That's what I'm hoping I have time to tell you about in the next few minutes. So we're going to define a map, call it pi sub t, from the singular set to the regular set. And what we want coming out of this is that pi sub tv is in reg. What's the role of the subscript t? We want that after we push it for time t, we're also in reg, and we want its trajectory along the middle, near the singular set, along the middle of the orbit. So how do we do this? Somehow the idea is that we start with an orbit segment in the singular set, and somehow we move the start of it into the regular set, and then with what we get, we move the end of it into the regular set also. That's the idea. I'll make that precise. So I can define reg eta to be the set of V, so that lambda V is greater than or equal to eta, and I'm going to fix a small eta 0, of course small enough so that this has non-empty interior. And the main thing that is helping us is density of the stable and unstable leaves. And with the density of the leaves, we can hit it with some compactness arguments and get some kind of uniform density in the following sense, that there exists a uniform R such that for all V in T1M, singular or not, the stable of size R intersects reg eta 0 is non-empty. So I'm just choosing R big enough so that every stable intersects the regular set in a uniform way. Same for unstable. Okay. So what's my construction? So my goal for the rest of the talk is to write down 2 sentences here and draw a picture. Then I'm out. So what's our procedure? Given V in the singular set, I'm going to choose a V prime through this method, which is in regular, and then for ft of v prime, I'm going to choose ftw belonging to the unstable and I'm going to define pi sub t of v to be w. That's what we did, and I think a picture will be in order. Okay, so let me see. So let's draw a, this is V belonging to Sing. Off it goes, and let's imagine that it's in the middle of a flat strip, just for illustrative purposes. So here's a flat strip. Here's V hanging out here. It's most definitely in the singular set. So what's my procedure? Well, this is WSR of V, and I know that if I go out far enough, eventually I'm going to be able to find my point W, which is in reg A to 0, right? So I'll draw it as a vector, okay? Okay, great. So what does this do? Well, this goes and it goes and it goes, and what it's going to do? Oh, this can be GTV. Well, this is going to approach the edge of the flat strip, right? Okay, and now I'm going to do this procedure with this point. So this point here is GTW. Now take the unstable of this guy. So this is WUR of GTW. And this is probably not in reg eta anymore. It's in reg, but I've probably lost all uniformity. But go back out again so that I'm back regular again. So that point can be, what did I call it? That's FTW, which is belonging to my regular thing again. And then what does this do? Well, trace it back. You know, it's going to start getting close to this guy, and it's going to end up near to here. And that's the point, whoops, that I declare to be pi t of v. Yeah?
You've got W was at the top, and then you went over to A to T of W.
Then I went over.
You moved up in the W in the unstable, and then you still had W.
This is v prime. Apologies, thanks, Keith. This is gt of v prime. This is ftw belonging to gt of v prime. Thank you. Okay, so things that end in this set have specification. We can use them to do constructions with. Along the middle, they're in the singular set. They don't get near in distance to V. That's a subtlety. They just get near to the singular set. And we can run this kind of construction. That's where we get the entropy gap from. In summary, I hope these lectures, we think there's a lot more to run in these techniques. So I hope these lectures have been helpful. Maybe some of the examples that you all think about can fit into this scheme. And I will stop there. Thank you. Thank you very much.
So, other questions or remarks?
The Drapier theorem, if you fix entropy expansiveness, is it necessary and sufficient for K property that the product is?
Actually, I'd have to think about that. We were wondering if it's just that you need the entropy map being upper semi-continuous. I mean, that's certainly necessary. It may be a little bit more. You need to know something about how things fiber. I'd have to check on that. I mean, it's one of those things. We had the assumption we needed that works, so we were happy. So it might be possible just to get away with upper semi-continuous entropy map, but certainly asymptotically entropy expansive is very general and works for us. Or maybe it is needed, I'm not sure.
Other questions? Okay, so thank you very much for this series of lectures.